And let's see how this works. Anyway, there's the backup of tomorrow's lecture in SOC. So if this doesn't work, I'll have another try. There is an advantage to actually teaching the class twice. So let's look at a little bit at the universe of programming languages. Let's start with that. Then we're going to look at the concept of language processing. And then we're going to try to go, but might not have time today. Oh, there's a clock there. Cool. Through the concept of inductive definitions, which are very important. They're a mathematical concept, not necessarily part of this course, but part of the background for this course, so we're going to have a refresher. Okay, and hopefully by next time I'm going to release the refresher on OCaml, and then till next time you will have the time to go through it and remember a bit of the OCaml you used to know, and we're going to be up to speed. So, what's in a programming language? So you see there are over 1,000 programming languages recorded in Wikipedia. I don't even know, there used to be a site many years ago recording all the programming languages of note, meaning that they weren't just the cool project of some kid doing a PhD, right? A programming language that was in some sort of use has created some sort of notable software. So it's over 1,000 programming languages so far. Why do you think there are so many?
These people create stuff like unknown C all the time.
Yeah, right. So it's a free world, right? That's the essence. Anybody, it's like freedom of speech. Nobody prevents you from creating your own programming language and use it. And I've actually created one when I was in Standard Chartered for financial products, a DSL. So not because because it had to be proprietary, so I couldn't use anything that was out there in open domain. So the drivers for creating programming languages are very varied. The problem is that people who have the need for a new programming language don't necessarily have the experience, right? And it's such a diverse environment that it's very difficult to pick the good ones, right? And then it's very much a popularity contest, right? So you will see that from the languages that are currently in use, not very many of them are well-structured, well-founded languages, right? They were created by people who, out of their frustration for some aspect of coding. So Python is an example, Ruby is an example. JavaScript is probably the worst example out there, right? Because it was created as a sort of cool add-on, and it took a life of its own, and it's uncontrollable now, right? But it reached a point where you can't ignore it, right? You simply can't ignore it. So everybody's trying to find some sort of a wrapper and sort of an isolation so that you have, the good programming world isolated from the bad programming world of JavaScript. You have a way of generating JavaScript without having to touch it. And I am in such a place. So I'm using a variant of Scala called Scala.js, which compiles to JavaScript, right? For this reason. But it's a big universe out there. If you look at forums and if you try to find out what people think about programming languages, you will find a diversity of opinion. There are many opinions out there from people with different backgrounds, each of them claiming a certain level of authority, right? And it's very difficult to say who's right, who's wrong, because it's a free world, right? What we're going to do in this module is take the classical approach, right? So thinking that languages have to come from a good background, right? A good paradigm. We're going to talk a little bit more about that. But let's look at the entire phenomenon a little bit first. So there's many approaches. Many of the approaches are religious. They address frustrations with the programming world that people have, but they address many other things, right? So, and actually that's part of the frustration. Software engineering concerns such as reuse and modularity, right? If you look at Python, for instance, it doesn't have a very good modularity system. It doesn't have a very good way of providing reuse of code. Languages such as Java were created on that wave, right? So people who were very frustrated with C++ started to think, what should we take away from C++? C++ at the time was very general. So what should we take away from C++ so that it becomes a useful language, right? And they came up with Java. But Java was much more than that, right? The main thing that was a concern at that time was these concerns of reuse, modularity, clean code to a certain extent. Large organizations face this problem where there's large turnover, people come and go. So you want to write code in such a way that a new person coming into a project can get up to speed very quickly. And there are ways of doing that. And you want to create a language that restricts people from writing code that is too smart. Because smart code is difficult to understand by people that are not necessarily very smart, right? And then if you're in a large organization, you don't have the luxury of hiring smart people all the time. So you want something that is the common denominator of all the coders that you have. So that's one reason. There are many types of programmer backgrounds, right? And there are many types of project management concerns. So the person who is ordering the software and hiring the programmers, they will say, oh, I don't want too much time spent on bugs. And even though they're not very competent in that, they will talk about and we'll find out, oh, in C++, you get this kind of crashes where there's no information about what crashed. So then they will say, oh, I don't want C++, I'm going to make my programmers write in Java because there you get a stack trace every time there's a crash, right? So that's a useful feature to a certain extent, but does that really improve productivity? That's hard to say. However, from the management perspective, right, they always want to have a feeling of control over how the project is going, right? And this kind of handles give them control. And often programming languages, and not just, entire software suites have been created out of these idiosyncrasies that the management has, right? Management in the software industry, you will be surprised to find out, often doesn't have a computing background, right? There are people who with business competencies, but not so much software engineering competencies, right? So they have a very strange way of looking at things. There's another one of addressing corporate branding needs, right? And Java, to a very great extent, was addressing such a need, was trying to create loyalty, right? Brand loyalty. So you would you would start using Java with its free environment, and then you would figure out that you need all sorts of other tools that were non-free, right, from Sun Microsystems initially and now from Oracle, and then you start buying into the whole thing, right? Then you also realize that you need more coders, and then you need to buy training from these companies, and it becomes a business, right? So Java was a very good business model for Sun. So good that Microsoft jumped on the same wagon later with C#, right? They created C# in exactly the same vein. And remember, creators are often very highly opinionated and with very strong vision, right? Programming languages are very often religions. You will often go and see debates. There are quite a few that were famous between Python and C++ in the days when C++ was still relevant. Why should you use Python instead of C++? With people attacking each other, literally, engaging into a flame war, trying to support their cause. These are always, my opinion, very dangerous. But in the end, you see, diversity in this world is what increases the need for software developers and what makes our salaries go higher, right? So you're aware that there's a huge hike on software engineers' salaries right now, and these kind of disagreements actually are contributing to that. So to a certain extent, it might be good, though if you're thinking purely from the perspective of creating solid, reliable, robust software, they're obviously not that good, because they're not encouraging, they're encouraging people to take sides from potentially technically non-sound perspectives. Right? Simply, I'm attached to Python because I learned it first, and I like the gang that I'm hanging out with, and we want to be proud Pythonists and so on, right? So you might choose Python for a project without Python being the right tool in that project. All right, so we're going to take the classical approach, right? We're going to justify the need for a programming language because there is a programming paradigm or a computational paradigm underlying it. One that is sound, has a sound theory, comes with, sound semantics, and so on. There are several paradigms that have been identified, and there are languages attached to each of these. The oldest is the one called imperative. Imperative programming, you might have heard of that. It's also sometimes called procedural. Essentially, what you do is instruct the machine to what to do at each step. This was very easy to create because everybody has gone through a computer architecture class, right? You know what an assembly language is, you know what a machine language is, right? So these were essentially mimicking the machine language. The machine language instructs the computer what to do, right? It's one instruction at a time, do this, do that. So imperative languages took sequences or sets of instructions and made them into higher level instructions, right? And but in the same vein, right? Each instruction would tell the computer what to do, right? Clobber a variable, store a new value into it, print something, read something from the keyboard. Everything is imperative. Languages like this, the first one was Fortran, and you surely know that. And we had YSC3208, Pascal. PL1 is one that I missed there, was in use in IBM for more than a decade. And the crowning achievement of this paradigm is C. Now, thinking that C was created in 1972, right? So essentially, that's where it stopped. Right, obviously C++, Java, they all have some imperative features, right, even though we call them object-oriented. Object orientation came as an extension of imperative. But C is the last imperative, purely imperative language. So that's where this evolution stopped. People figured out that it's not good enough. So they went into object-oriented programming, right, which provides... So by the way, the distinguishing feature here is assignment, right? The fact that you can assign a value to a variable, that's the most imperative thing you can have. When you move to functional programming, you're going to see that assignment is actually not needed at all, unless you have concurrency. But it's generally not needed at all. And yeah, you can code without assignment at all. This is why imperative programming has assignment as its distinguishing feature. Object orientation is an extension. It encapsulates data into objects, right? This is a very simple thing to understand now. It's strange that it took the world so long to come to the concept of an object. The distinguishing feature here is inheritance, right? Inheritance is a very sleek way of providing reuse, right? It provides reuse at a very fine granularity level, with very fine granularity. As it turned out, over the years, inheritance is not such a great tool, right? So it can be very easily overused. If we go back to the previous slide, when we talk about software engineering concerns, right? Inheritance is too clever a feature to be used in large-scale projects. It should be confined to very small pieces of code that are in the purview of some very smart people who continue to want to maintain it, right? Those parts of the code are not the ones that you want to change hands very easily, right? It shouldn't be in a project where programmers change very easily. And I'm probably telling you things that are very remote for you. You haven't really worked. You haven't worked in a large organization. You don't quite understand how things work there, how information travels around in a large organization, right? So you have to understand that getting agreement on anything is very difficult. There's a lot of communication. There's a communication overhead. In order to do anything and know that you're doing it right, you have to get the agreement of many, many coworkers, right? People get fed up and leave. And then in a large organization, the organization says, we don't want to lose you. So if you don't like your team, try to transfer to a different team. And there are constant attempts of people trying to change between teams, which means that any particular team doesn't have the same people for more than a year. And I'm proof to that, because I didn't stay within the organizations. I actually changed organizations every year after I left academia. All right, so more about this later. Functional programming came up very early with Lisp, right? So people figure out that at the time, one of the main formalisms of computer science was the lambda calculus. You know what lambda calculus is? Lambda calculus is an algebra for describing computation. It was created by Alonzo Church. You should Wikipedia it. It's really well described there. But once you learn OCaml really well, if you go there, that's going to be easy peasy. That's way simpler than what OCaml is. But that was the inspiration for the language Lisp, right, which appeared pretty much at the same time with Fortran in the 1950s. Was invented by a guy in MIT called, anybody knows? John McCarthy, right? Who died recently. Yes, you have a comment? Yeah. So it was followed by Scheme, which also appeared in MIT. These two are untyped functional languages. Scheme has a very good book called Structure and Interpretation of Computer Programs. We used to teach a course in NUS 10 years ago. So when I joined NUS, that's the first course I taught. Based on that book came Scheme. Then, somewhere in the 70s, ML came along. ML stands for meta language. It was a language built to further build theorem provers, right? So there's this specific area of computer science called automated theorem proving, right? There are a bunch of tools, and ML was created for that by a guy called Robin Milner, who also died recently. People are dropping like flies nowadays. So, and it was used to create a theorem prover called LCF. That's less important right now, but it spawned an entire family of languages. This ML. So it influenced OCaml, it influenced Scala, it influenced Haskell. By the way, OCaml and Haskell both used for theorem proving, right? So it seems like as a new functional language comes along, somebody would want to build a theorem prover, as it happened with ML. OCaml has one called, do you happen to know? Coq, very good. COQ, it's a French endeavor, pretty much as OCaml is. OCaml is a French endeavor. It came out of INRIA in France. INRIA is an institute, is a research institute. I might remember the French name, but not so important right now. Haskell, the theorem prover for Haskell. Anybody knows? Agda. Anyway, you can Google. Scala doesn't have one. Huge differences between OCaml and Haskell. OCaml is strict. Haskell is lazy. Scala is both. Scala is also object-oriented, and it's object-oriented in a very strong way, right? So it's mixing object orientation and functional programming in a very how to say, right? You can't do one without the other. which is a very fresh and novel approach, and which is why it seems to be so successful. So most people call it a functional programming language, Scala, but it's very much object-oriented as well. It's exactly at the crossroads between the two. Last paradigm is logic programming, which uses logic inference as computation. It has some distinguishing features which are very strange: unification and backtracking. The main programming language is Prolog, and it's a very interesting language going out of fashion. It's a language that was the main language for the 5th generation computer systems in Japan. Japan had this this huge project lasting about 20 years, starting from the 80s till the end of the 90s, right? Roughly 20 years. With a lot of funding, they were supposed to create the next generation of computers. At that point, it was said that computers were 4th generation, and they were trying to move into the 5th generation, and that was supposed to be an artificially intelligent computer. So Prolog was seen as the language of artificial intelligence at the time, and then a lot was invested in Prolog. Prolog has a huge potential, right? But out of 20 years of research, it produced no concrete results. So as a result, the language dropped in popularity, and I'm not sure anybody, anybody really considers Prolog. As a young computer scientist, they would consider Prolog as learning Prolog. I was active in that project, so I happen to know Prolog very well. It also contributed to something called constrained logic programming. I used to teach a constrained logic programming class till I left, till 2012. That was the last year. There's another aspect related to programming paradigms, which is concurrency, which is sort of orthogonal to everything else, right? So the way these languages handle concurrency is important, right? To what extent are they first-class citizens, right? And that's one important thing that will recur. What's a first-class citizen? It's something that you can put inside as a parameter to a function or a procedure, right? So, for instance, think about it. What can you put? Thinking of the languages that you know, what can you use as an argument? You can use obviously an integer or a string, but sometimes you can use a function. So the function in some languages is a first-class citizen. Right? And can you use a thread, for instance, or can you use an actor, which are concurrent constructs, right? And in some languages you can, in some languages you can't, right? So that gives you the level of to which a language is concurrent. There is a very early language which handled concurrency very well. It's called Erlang. It was derived from Prolog, and therefore it's not so popular anymore. So its Prolog background didn't help. But Google came recently with a language that is very highly concurrent. It's called Go. Golang, they call it now, because Go is too short a name. It's a very interesting language. It's up and coming. Google has a few projects in this language. It doesn't seem to be a language that is targeting corporate loyalty. So it's very much unlike Java and C#, which are trying to confine you inside a closed universe, but rather it's a completely open framework. And it's probably a language worth using. In Singapore, there are a few companies that are using Go, most notably Grab. Are you aware of the startup scene in Singapore? Yeah, so Grab is using Go. There are a few others, but probably less notable. Okay, so other well-known categories, scripting languages. This actually seems to be a very wide category. Python, Ruby, JavaScript. There's many more in this category. Generally, they're very hard to pinpoint what kind of languages are they. Because you see, they're not entirely scripting. Scripting would be interpreted, right? You would, at least, coming from with my background, when I hear scripting languages, I understand interpreted. Actually, Python nowadays is compiled to a virtual machine. It has a virtual machine, right? So it is compiled code. So is Ruby, and so is JavaScript. Actually, it has just-in-time compilation. So they're no longer simply scripting languages, but they're languages that are very difficult to put in one of the paradigms because they're trying to be multi-paradigm. They take various bits and pieces without taking the concept completely, and often that makes them quite confusing, at least from a person who is classically trained. The up-and-coming category is domain-specific languages. These are very narrow languages, very niche languages. They look at a very specific aspect of computation and try to do one job well. And because of that, most often they are embedded. You have a bunch of examples. They are by no means it's by no means extensive or exhaustive. The last three that I put there, it's stuff I've worked on, and it's stuff that is typically proprietary. People don't like to release that kind of stuff in the open domain. They think they have the intellectual property will give them an edge with these kind of tools. I'm not sure to what extent that really works, because there's a lot of reinventing the wheels whenever companies decide to do these things and keep them to themselves. But nevertheless, these are there, right? So the tool, the skill of designing a language, especially for a domain, is in very high demand nowadays. So this is worth something. This is something that is worth learning well. Cool. Any questions so far? All right. So this is more of a introduction. Let's look a bit at language processing. Try to understand a notation which we call T-diagram that will hopefully shed a bit more light on how things work in language processing. So let me start with one very simple thing, right? We all understand the concept of translation, right? We at least know what it means for a natural language. I take English and I can translate that into something that has exactly the same meaning but is in a completely different language. We all know that it's possible. Now, all of you know at least two programming languages, and you know that it's possible to write a piece of code in one of the languages, right, and compile it or run it, and then as you look at it as a black box, running it from a terminal, right, you see a certain behavior, right? Maybe it prints a string asking for some input, you provide that input, and then it provides a string that contains the output, right? And then you can rewrite that in a completely different language and make it have exactly the same behavior, right? So that if you run it from a command line, you wouldn't know in which language it was written, right? That behavior could not indicate in any way what language was used there. So the question is, can this be done mechanically, right? Can I take this and can I put this source in one language through a tool, right? So this tool is a piece of software. And now my program, what was previously a program, is data to this language. So there's a paradigm shift. Because what previously was a program, it's still a text file, right? But it's a program to us, right? Conceptually speaking. But I have this software tool called an interpreter or a compiler. And then this, what I thought initially as a program is now data to the compiler, right? So that's an important thing to understand and remember. And yeah, the question is, can this be done mechanically? And the answer is, of course, yes. I can translate from C to Java, from Java to C. The most important type of translation is from a language to machine code. Now, when you hear machine code, to many that seems a bit scary, right? Machine code is just a language, right? The machine instructions are just part of a language, which is no different. It has less power, meaning that each instruction has very little power, but nevertheless it's just a language. And you could write that into a file, which is the binary file, and that gets loaded, and the interpreter for that code is the processor. All right? So the processor is in fact a language processor. It's no different from any other kind of interpreter. But that's where the entire string of translations ends. Once I have a language that is directly interpretable by hardware, I can just take that and execute. Right? Before I get to that point, I have to go through multiple sequences of translations to produce that kind of thing. Right? And these language translations are going to be our business. So we're going to use some symbolism. That pentagon over there at the top, that's the processor. And we're going to look at a variety of processors. So 5x86 is one example. But here we have a more generic one, right, which is x86. x86 can execute code for the 5x86 processor and more. Now I can have a program called Fibonacci, computing the Fibonacci, that is written directly in machine code. Right? Meaning I took the specifications manual for the processor and I assembled all the bits together, and I came up with a sequence of zeros and ones, and I put that into a binary file, and I can load that from memory into memory and start executing it, and it computes Fibonacci. Right? So the execution of the Fibonacci will be represented as this thing, right? And notice that whatever I write here at the bottom has to be the same thing as I write here, okay? But I could actually use the fact that one processor is more generic than the other, and I could write 586 here. So if I have the Fibonacci written in the language of 586, I could put it on any x86 architecture and run it, right? But there has to be a correspondence at this level. We're going to see that these correspondences are quite important. So this is pretty much what I just said, right? We're in the business of translated languages. We call them the from language and the to language. The compiler translates from high level to low level, and so a translator that translates from high level to low level is typically called the compiler. We can also have the reverse, which is a decompiler. Most decompilers are illegal, at least for proprietary languages such as Java and C#, but it's nevertheless possible. And they're not useful unless you're trying to reverse engineer stuff and essentially try to steal intellectual property. Otherwise, it's easier to just ask for the source and look at the source. Now, we have an element called translator, right? So let's say we want to translate from BASIC to C. So this is a piece of software whose input is a BASIC program, right? And it's again the business that we were talking about previously. For us, the BASIC program is a program, but for this tool, the BASIC program is a piece of data that is the input. And we'll produce a piece of output, which is another file, which is the C program, right? And this translator runs on x86. Has been. So this translator is a program, right? In this represents just the software, but if here at the bottom I would add the pentagon with the x86, then I would have a running program. That would represent the running program, not just the software, but the software in its running state. And what is more typical is that these two things are the same, right? So let's say we have a OCaml native compiler, right? Takes the OCaml code and produces x86 code. But this entire software is also written in the x86 machine code. And it's actually not written, it was produced by another compiler. And we'll see how things can be expressed to show that. Now, not all code is executed natively, right? Some code is executed on virtual machines. The virtual machine has its own language. OCaml has a virtual machine language called bytec. So OCaml comes in two flavors, actually. A flavor that compiles natively and another flavor that compiles to the OCaml bytecode machine. We call it bytecode. And this is how it is represented. Input is an OCaml program. The output is a bytec program. And this entire thing is written in x86 machine code. All right. So now we can build somewhat more complex diagrams, right? I have my Fibonacci in BASIC. I plug it into the BASIC to C translator, which is running here, and I'm going to get a Fibonacci written in C. Fibonacci is not running, right? What is running is the compiler that takes Fibonacci in BASIC to Fibonacci in C, right? Notice the correspondence. We have BASIC here and BASIC here. We have C here and C here. We have x86 here and x86 here, right? Things work only when used in the right environment. And we can do it in two steps. Take BASIC to C, and then take C to x86, and then we would have a Fibonacci that can run on the x86. It's not yet running according to this diagram, but can run, right? So this element here can run on x86. Is this clear? Pretty straightforward. So now we can compile the compiler. Okay. So that's when you start asking what came first, the chicken or the egg. So you have a BASIC to x86 compiler written in C, right? So this thing translates BASIC to x86, but this is a C program, right? This is a C file. And having it as a C file is not useful to me, right? So I have to convert the C file into something that I can run, right? So I translate it from C to x86, right here, right? And to do that, I have to have this compiler running on some machine, and it can be x86. By the way, these two don't have to be x86 all the time, right? I can do something called cross-compilation, right? My purpose is, at this point, to obtain a file that I can dump into an x86 machine and run. What's the result of this? The result of this is a program that takes BASIC to x86, so exactly the same thing as here, right? But now it is written in x86 code, right? So think of the following. What if instead of BASIC I would have C here? Is that possible?
Yeah. When you get a C to x86 compiler written in x86,
right. So the question is, if that's the case, right? What do I compile the compiler with? Right? So think of how things evolved, right? Let's say that C was the first programming language. Before C, there were no compilers, right? All we had was machine code. So people were programming by...
You can handwrite x86 code.
Yes. So the first compiler that you write of C is in x86, right? Then, so that's version 1. Version 2, you write C in C. How does that work? Well, you have the x86 compiler that you wrote as version 1, right? So you can use compiler version 1 to compile version 2, but then guess what? Now you have a version 2 compiler in binary, so you can compile version 2 with version 2. So that's an essential step in bootstrapping a compiler. If you look at GCC, GCC does the following. First of all, it uses what's already installed on your machine to compile the new version of GCC. Then it takes that GCC and replaces the old GCC, and then it recompiles itself again, right? Because it takes advantage of all the improvements, right? Because you want the compiler binary to take advantage of all the improvements that are capable, that the new compiler is capable of, right? So, an important issue. Is this clear? When I used to teach this class, I had a much bigger class 6-7 years ago. That was a major sticking point, right? So people would come at the end of the class and say, what's this? Yes?
So is the GCC written in C?
Yes, of course. So the first version of GCC was not written in C, of course, right? It was written in some machine code, some assembly language or machine code at great expense, right? With a lot of effort. But once that was available, people said, we already have a C compiler, so let's throw away the machine code, right, and write the new version of the compiler in C. I can use version 1 to compile version 2, But guess what? When I have a version 2 binary, version 2 can compile version 2. Okay? So actually, this is what I'm representing here with OCaml, however. Right? So OCaml can compile itself. And it's a necessary part of bootstrapping a compiler. Okay? So I have an OCaml to x86 written in OCaml. All right? And I already have a previous version of OCaml, of a OCaml compiler, that takes OCaml to x86. So I produced the new version of the compiler. Cool.
The diagram is a bit confusing because you don't have like the versions written up there, but
Yeah, so that would be a good thing to add. Right? But it nevertheless works because even at any point you can a compiler can compile itself. Right? Most modern languages make the point of being written in the same compiler being written in the same language. Right? So Camel, that's the case. Haskell, that's the case. Scala, that's the case. C#, also written in C#. All right. So we're distinguishing between several classes of language translators. One is an interpreter. An interpreter is a program that executes another program, right? And we already saw an interpreter, which is the processor itself, but we can write other interpreters. A lot of languages are interpreted, especially scripting languages. It depends on the version. Node, for instance, will interpret JavaScript rather than compile it, though browsers do just-in-time compilation of JavaScript. The interpreter will have a source language, and in general we talk about source languages and target languages in program translation. It's pretty clear what they mean. Yeah, so that's what the interpreter is. Basic is a typically interpreted language, though not anymore. So Visual Basic is not interpreted; it's compiled. OCaml, you could say that its bytecode is interpreted, right? But OCaml is typically compiled. And whenever we talk about interpreting a program, we represent it with this diagram, right? We have Fibonacci written in BASIC. We have an interpreter of BASIC running on x86, and then we actually plug it into the x86 architecture when we get a running Fibonacci program, right? So interpretation diagrams, they're generally vertical, whereas compilation diagrams are mostly horizontal, right? You take a language into another language into another language, and you get something that is runnable at the end. This would be hardware emulation, right? We have Fibonacci written for x86. We have a virtual machine on an MPC 7450 processor that emulates x86 instructions. And then we have an MPC 7450 architecture processor, right? So we plug that in and we get a running Fibonacci program. All right. Java and OCaml also has this, it's possible to do it for OCaml. So Java is running on a virtual machine, right? So it has interpreted bytecode. So what we have to do here is perform a compilation from Java to the JVM code, and then interpret the JVM code, right? So we have both steps. I was saying that compilation, this is compilation, it's mostly horizontal, and then interpretation is mostly vertical. In the case of virtual machine languages, we have to have both, a little bit of both. Advantages for using a JVM, we're going to go into that soon. Remember that is just currently we're just exploring it as a possibility for language processing. How did we make these slides? So I take the slides for this lecture, which are in LaTeX. And there are three processing steps, right? And I produce a PDF version. So there's a compiler from LaTeX to DVI. It's called device independent, right? That DVI is further translated into PostScript, and that PostScript is further translated into PDF. All right. So same thing using LaTeX, which is a domain-specific language. How are we viewing the slides? So what's happening right now is that the Acrobat reader is like a virtual machine for PDF. PDF is like an interpreter for PDF. All right. So we are plugging the PDF version of the slides into the PDF viewer, which runs on x86, and this allows us to view the slides on the screen. Okay, so I think I'm gonna pretty much stop here. I think the next part is the inductive definitions, and I'm gonna save them for next time, when I'm gonna also come with some examples, and we're gonna get our hands a little bit dirty, running some OCaml code. But what did we look at? Generally, we looked at the business of language processing and language translation. We learned about T diagrams. My main purpose there was to talk about the compiler bootstrapping itself and show that there's this relationship. What conceptually is a program for us is actually data for some language processor. That's something worth remembering. Nowadays, it's typical to have a combination of interpretation and compilation. Compilation alone is not so cool anymore. They're good skills to know, right? Especially because DSLs are nowadays so common, and the need for designing new ones is quite high. All right, so I'm going to try to keep my lessons to about 10 minutes, 1 hour, 15 minutes. I understand that, you need time to move to another class typically. So there's still a few things to clear for me, generally how I get in touch with you. But in the meantime, just to be on the safe side, so I can send you materials, send me an email, each of you, so I can get a mailing list, and then I'm going to send the slides. Also, probably by next time I'm going to have the video recording for the OCaml refresher, so I can send you a link for that. I'll probably upload it to YouTube. It would be good if you can watch it before next week at some point. You're comfortable enough with OCaml that you can install your own OCaml. I don't need to give you instructions on how do you find OCaml, how do you install it. Yeah, it's all good. What operating systems are you using typically? So there's a Mac. The other ones are Windows?
Yeah.
Okay, cool. Okay.
So I used to use Windows, but my laptop just died, so I'm getting a Mac next. So I'm not sure if I'm comfortable installing OCaml
There's
on
two
Mac.
guys missing and they're on Macs.
All right.
So three
Cool.
guys.
Yeah, I'm mostly on Linux actually, but I do have all. So this is a Windows machine, that's a Mac, and but my main desktop is Linux. But yeah, so I'll try to test everything in in all environments before I release it, so that there's no surprises. Anyway, so I mean, my experience with OCaml is that it's pretty straightforward to install, so there shouldn't be any surprises at that side. And then we're not going to do anything. Everything is going to be command line and file input, file output. So there shouldn't be any surprises there either. Okay, questions?
I'm still a bit confused about how interpretation works exactly.
Mhm.
Compilation, I get, like, translates it, like, say, 86 and runs it, but like, how does the interpreter work in, like, in real time? Like, how does that? So does it like compile line by line and then execute that, or?
No, it can take the easiest way is to not do everything as it happens, right? Which is what typically happens with I think JavaScript and JavaScript at least. So only the parts that, for instance, that are executed are compiled. It happens to be, I mean, you can think of JavaScript as being interpreted, right? So if you have a syntax error somewhere in the middle, but that code doesn't get to be executed, typically your program runs fine, right? So what you do is you build some internal representation of the syntax, right? And execution is the syntax, the structure of the syntax is a tree, which we call a syntax tree. We're going to see that soon enough. And then execution is just a tree traversal, right? So you start from the top, right? The left child of the top will be the first statement, let's say, right? You go there, you see what it is. Oh, it's an assignment, right? So then it's an assignment, it has a destination, and it has a value, right?
Yeah.
So you compute the value, you put it into the destination. You keep a hash map of all the variables in your program, right? And then you go back, you do a depth first traversal, right? You go back, you go to the second child of your root. What's that? It's a print statement, right? Then you go and print. So you have this big program that traverses the tree, and then at each node it figures out what it needs to do, right? So now this tree can be constructed on the fly, or it can be constructed and stored away, and then the execution just traverses the tree, right? So obviously the second alternative is faster, right? But there's a lot of interpreters that don't do that. So Bash, for instance, doesn't do anything like that. Bash is simply, processing the file, the input file, the script, right? One line at a time, just going through, not caring too much about the structure, not trying to create too much of a tree, trying to just go back. So for instance, it comes to a while loop, right? Or a for loop. It just holds a pointer to the last encounter for loop, and then every time it hits the end, the done, right? It just looks into a stack, what's my most recent for loop, and it jumps into the text file there, and it starts reinterpreting the text file and redoing all the lexical analysis, right? So it's essentially very inefficient, but it's very simple in that way. So it quite varies, so to speak. Interpreters are a lot easier to write because they don't require knowledge of a target architecture or a target language, right? If you want to write a compiler, you have to know assembly language, or you have to know whatever target language is. If you write an interpreter, all you need to know is the current language that you're coding in, right? So it's generally a lot
Wait, but like,
easier.
When you say you have to know just the current language that you're coding, you still have to convert the interpret it to something else, right?
No.
Yeah, but that's being done by the processor for whatever language you're coding in.
Right.
So let's say that in your original in your interpreted language, right, you have a print statement, but in the language that you use for the interpreter, print translates into write. So you're going to look down the tree and you're encountering the word print, and then you say, oh, I see print, so I have to write something out, and you use the write instruction of the current of your interpreter language to execute the print statement of your. Okay. So you don't have to translate really into anything. It doesn't require knowledge of an extra language, whereas compilers do. That being said, if you have that knowledge, to me, writing a compiler is a lot easier than writing an interpreter. Just because, we're going to go there, right? So, because compilation requires a single traversal of the tree, right? So you create this syntax tree, right? And at every node, if actually I have actually need to give past past 10:20, but let's see if I can use this. I don't know why it's. All right, so you would have a tree, right? So let's say this is a while node, right? And then here you would have a condition which is maybe less than, and you have an x, and you have a y, right? And here you might have a body, right? So you may have the semicolon as a node, and then here's an instruction. I'm going to just call it I1 and I2. Right, this would be while x less than y, open brace, first instruction I1, second instruction I2, right? So if you're doing compilation, you're doing a tree traversal, but you're doing a tree traversal, so you know tree traversals, prefix, postfix, infix, right? You're actually doing a combination of them, right? So for prefix, you're doing something while you reach the node and then you visit. For infix, you're doing left child and something in the middle. So here you're going to do something. You're going to do an action just as you arrive at the node. You're going to go down the tree, and this action actually generates a piece of code into the object file, right? Into the destination. You're going to, each of these will have the same kind of thing, right? And then you're going to generate all the code for the subtree. So this will go in here. Then you're going to have an action that goes in between. So this goes here. And then you're going to have all the code generated by this, which is bigger, and then you're going to have an action that you do at the end as you leave, and this is going to be, you're going to put it there and here, and this is the binary file. All right?
Yeah.
So now giving you this, you can actually spend a little time and think, what would you put here, right? What would you put at here, here, and here for each type of node, so that this becomes executable valid code, right? And you're going to figure out that it's not that difficult to find out these things, right? We're going to discuss these things, but it's actually, this is all the philosophy that you have to understand, right? Whereas if you're doing interpretation, you're going to say, oh, I'm here, I'm going to down this path, right? I'm going to evaluate this and decide where I need to go and evaluate this path or not, right? After I finish this, I have to go down this path again, evaluate this again, and I have to see whether I have to continue, right? So I have a much more complex traversal. Right?
And you're doing a lot more work.
Yeah, so you're going to go up and down this tree a lot more, right? So it requires a bit more mechanics to do it. So for me, it was always, easier to think in terms of compiler, which is a one pass kind of thing, rather than. I need to fix this and have the slide not shrink when I go into this drawing mode. Anyway. This is about it for today. I'm not quite sure what's happening. So yeah, I think you should go ahead, and I'm going to try to